In this section, in this video, we're going to be talking about parametric equations and the plane curves that go along with them. Okay, so let's look at a function, maybe a parabolic function, and let's say that goes along with the equation y equals negative x minus 2 squared plus 4. It's a parabola with a vertex 2, 4. It opens down. And maybe let's say we're only looking at it on the interval from 0 to 4. So if I drew my axes in here, it would look kind of like this. If I can get my aim right. Now, while this picture and this parabola, we can answer a lot of questions about it. We could talk about domain here that we're looking at. We could talk about the range. We could talk about the highest point that it hits or where it is when x equals 3. But oftentimes, when we're looking at a situation and looking at a curve, there's more to the story than that. Okay. Maybe this came from me kicking a soccer ball off the ground and it went up into the air and then it came back down. And so I not only can visualize the trajectory of that ball, but I maybe want to know, um, how high in the air it was 1 second after I kicked it, or how long it took for it to hit this highest point. Not that it happens at x equals 2 and y equals 4, but at what point in time did it hit that? Or how long did it take for it to land on the ground on the other side of the field over there? So when we introduce that third variable, we call that a parameter. And what we can do is then look at what we call parametric equations. Okay, and maybe here in a little bit we'll come back to this particular parabola. But right now we're going to make a definition that says we need to have, there's my cursor, two continuous functions. Okay, our parametric equations always involve continuous functions, at least on some interval I. Then if we look at the set of ordered pairs, f of t, g of t, for all the t's on I, that creates, if we plot those points and sketch that graph, that creates what we call a plane curve. Now, not plane like boring, but A-N-E here, not like an airplane either, but plane is in, it falls in 2 dimensions, so it falls on my board, on my computer screen, on my whiteboard, my chalkboard, whatever. When we talk about parametric equations, it's when we look at our x coordinate as a function of, and t is the most common parameter. We'll use thetas if we're talking about angles, but t doesn't have to mean time, but those are the most common examples. Is that the parameter is time. But if we look at this set of equations together, this is our set of parametric equations. And again, t or theta or whatever our third variable is other than our x and our y, that's our parameter. So let's say we're given the set of parametric equations, x equals square root of t and y equals 3 minus t. Let's say they tell us that we want to, I'll say belongs to, let's let t be the interval from 0 to 4. And maybe the request is that I sketch a graph of this plane curve that goes along with that. I'm going to pause for a minute and find my axes. I'm going to make, okay, voila, axes. When we're sketching a graph, the best way, especially if something is new to us, is to do what we've done all along, and that's just plot some points. So maybe since I'm looking between 0 and 4 for t, I'll let t be 0, 1, 2, 3, and 4. Then I come down here to each of my equations and I plug in and I see what comes out. So the square root of 0 is 0. The square root of 1 is 1. The square root of 2 you could write as a decimal. Think about what that is when you go to put your dots on the page. But square root of 2 is around 1.5, not quite. Square root of 3 is between 1.5 and 2. It doesn't have to be perfect when we're just sketching a graph. You shouldn't put it between 2 and 3, but you should get them between 1 and 2, those dots. For y, if we take 3 minus 0, 3 minus 1, 3 minus 2, 3 minus 3, 3 minus 4, we have those values. So if I want to draw a sketch of this curve, the plane curve that goes along with these parametric equations, my first ordered pair is the ordered pair 0, 3. So x equals 0, y equals 3. So then it goes through the point 1, 2. It goes through the point square root of 2, which is just less than 1.5. 1. Square root of 3, 0. Square root of 4, which is 2, negative 1. Make these dots kind of big so they take up, so I hit the right vicinity. Okay. Now, when we draw the plane curve, we are going to include orientation. When t equals 0, we were at this point, and then we slid our way down to this other one. I'll try to make that curved on my little tablet that doesn't like me. And once we have connected those dots, we're not going to continue and say, whoo, it goes on forever. Not if we are told that t has a maximum value. So we stop when t equals 4, which was the point 2, negative 1. We started when t equals 0, which is the point 0, 3. And we put little arrows on there to indicate that this is the movement of my whatever it was, instead of it going this direction. The good news or bad news about parametric equations, it's kind of like when we were back with angles. There's an infinite number of ways that we can write this curve right here using parametric equations. Okay, this is not unique to this situation or to that curve. It might be unique to the situation that we're describing. So on your paper at home, let's look at this set of parametric equations. X equals 4 cosine squared theta. Instead of a t, I'm going to write a theta. If you like t's better, you can call it t. And y equals 2 sine theta. Let's let theta belong to the interval between negative pi over 4 and pi over, is that true? Negative pi over 2 and pi over 2. I thought that seemed kind of small. I want you to draw a sketch of that graph the best you can. Let's plug in the points negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. Okay, of course, if you wanted to be even more specific, you could pick things like pi over 3 and pi over 6 here in between, but that'll be enough to get a general idea of what that shape makes. So pause the video, find your x's and y's, plot them. I'm going to put a graph over here and see what it looks like to you. Because we're squaring the cosine, before we take it times 4, don't forget to take it times the 4. But all of the x-coordinates are going to be positive. When we're in the fourth quadrant, our sine function is going to be negative, and in the first quadrant, we're going to be positive. Okay, go ahead and go back and plot the points now if you haven't already. If you need to correct something, then pause again, get things fixed, and then draw your graph. Here's our dots on the page, and since we started here with our theta, I put a T on my graph, but I'll change that here in a minute. We moved around this way. Okay, so that would be the general shape, and again, we don't continue on and put arrows there because we're only looking at this range of values for theta. Okay. Notice that when we sketch a graph of a parametric equation, this one versus the other one, that this one was a function Okay, and this one's not a function. It doesn't pass the vertical line test. But our graphs, we can still describe them and talk about them being parametric equations. I don't think we call them functions, but if we do, each of these is a function. And when we put the picture together, we don't always get one. Okay, next video we'll pick up with the next idea.